Preview where we left off last time. We were in chapter 4, and we were discussing 2D conduction, and we did some problems involving 2D geometry, which were sketching problems, sketching what's called a flux plot, which was the isotherms and the adiabats. And we did that, and from that we got an estimate of the temperatures and the heat transfer in that object, that 2D object. And then we jumped into table 4.1 and said, a lot of problems have been done for you already. The results are listed in table 4.1 with something called the conduction shape factor S. And there were, I think, 12 to 15 cases in table 4.1. We talked about a couple of them. One case, case 6, looks like this. We're going to use that for a problem right now. So what you do, if you've got a geometry that looks like something in table 4.1, you get the conduction shape factor, capital S, with some restrictions, and then you can model that by a resistance 1 over Sk, K being the thermal conductivity of the material. Okay, so we're going to use that on an example here, similar to homework, problem 431. Let me go ahead and read it. There is a picture given with problem 431 in the textbook. There is a hole a 1/4 meter in diameter. So D is a 1/4 meter in diameter. It says, a solid block of square cross section, 1 meter on a side, 1 by 1 meter. A hole drilled through the block, 1/4 meter in diameter. The material of the block has a K value of 150. There's convection on the outside of all 4 sides. Convection to air, air's at 25 degrees. Convection coefficient 4 watts per square meter degree C. On the inside, there's also convection. I'm going to put that in here. The inside, the temperature, T infinity inside, and H inside. This is H outside, O for outside, I for inside. Inside temperature carries hot oil. Temperature of the oil, 300 degrees C, H is 50. Okay, H is 50. And let me just check real quick in the appendix. Oh, yeah, okay. K could be some kind of maybe stainless steel, that K. It's a metal. It's a metal, probably. Stainless steel. It's a little bit too small for a carbon steel. Oh, nope, I take that back. 150, not 50. It is a carbon steel. All right, so anyway, we have hot oil going through a hole in a carbon steel block. Air on the outside. We're at convection on the inside of the oil. We're asked to find the heat rate. Let me make sure. Yeah, find the heat rate. Now don't forget, we've got Q, Q prime, Q double prime, Q dot. Which Q does he want? He said the words, heat rate. That means Q. What's Q in? Watts. He wants the answer in watts. He also says to find the surface temperatures inside and outside. Okay. Well, it's a 2D conduction problem, obviously. By the way, he also says the length of this thing is 2 meters. Looks like that. Okay. We're going to go back to Chapter 3, review it for Monday's exam. We're going to draw the thermal circuit for this problem. We, as we said before, normally start off with the hot temperature. Okay, oil, 300. Hot oil to the inside surface of the circular hole. Convection, R, convection on the inside. Then it goes by 2D conduction to the outside. Conduction. Then it goes by convection from the outside surface to the free stream of air, 25 degrees C. Convection. Then they're in series. The resistors are in series. So the heat rate is Q. As we said before, when you draw a thermal circuit, label everything. Label all the resistances. Yeah, they're labeled. Label the temperatures. I'm not done yet. I'm going to call this guy T. This is on the inside. I'll call that T inside. That's the temperature where my finger is on the inside surface of the hole. Temperature on the outside is temperature of the outside for 1 meter surfaces. And Q is labeled. Okay, label the heat flows, Q. Label the nodal temperatures, I did. Label the resistors, I did. Now do what they want. First of all, find the resistances. R convection on the inside. 1 over H inside, A inside. This is right here is H inside. I know what it is. It's right there, 50. The area on the inside, though, the area of the inside, it's a circle, hole, pi d times the length L. Okay, R convection on the outside. The area of the outside, there's 4 sides, top, bottom, left, right. Each area is 1 by 2. 4 times 1 times 2. Okay, 0.1273, 0.01273. That's on the inside. I got to flip-flop. This guy is this one. A outside is 50. Yep. And so let's put the inside one. The inside one, H is, I'm sorry, the outside one, H is 4. Did I get that right? Let me see here. 50. 50 is the inside. Yeah, I had it right the first time. And now the H on the outside is real small, 0.0625. Okay, and the third resistance is R conduction through the 2D body. Okay, remember what we did over here. I'll just remind you again. We said you can model this by a resistance with a heat flow Q with T1 and T2. And that resistance is 1 over SK. Okay, we put that resistance over here, 1 over SK. All right, have to find S. For this geometry, S equal 2 pi L. Let's just put the numbers in. L is 2. Divided by natural log 1.08 times W, 1, divided by the diameter, 2.5. S comes out to be 8.58. Okay. So S is 8.58. So that resistance for the conduction so if I compare those three resistances, I can see, wow, that conduction resistance is really small. The biggest resistance is convection on the outside. Yeah, that's the air side. That makes sense. Okay. Once we get the resistances, now we get the Q. Q equal hot temperature minus cold temperature, 300 minus 25, divided by the sum of the resistances. So the heat flow from the hot oil to the outside, 3.62 watts. Okay, got it. Find the surface temperatures inside and outside. Okay, look at the picture. I want to find TI and TO. Okay, like the heat transfer equation from 300 to TI. Q equal hot temperature minus cold temperature divided by the resistances between those two temperatures, or convection inside. Solve to get TI equal 254 degrees C. If I want to get T on the outside surface, I can start at 300 and go to T outside, or if I want, I can start at T outside and go to 25. I'll go that way, a little bit easier. So Q equal hot temperature minus cold temperature divided by resistances between my two fingertips, or convection outside, 0.625. By the way, what about that Q? You put that Q in here, and you put that Q in there.
Shouldn't that be 3.62 kilowatts?
Which one? Oh, yeah, it should be, thanks. Solve to get, let's see what we get here. T outside now, that's the four surfaces of 1 meter each, 251. Look how close those temperatures are to each other. At the inside of the material, the temperature is 254. The outside, 251. 254 here, 251 here. Not much change in temperature. It must mean the resistance is pretty low. We'll check conduction. Oh yeah, the resistance is pretty low. Compare this one to that one. 100 to 1. 100 to 1. So yeah, there's not much temperature difference across that metal block. Okay, did we satisfy the conditions for S? Was W greater than D? W was 1, D was a quarter. Yeah, that's right. Is L much greater than W? L is 2, W is 1. No, not really. Much means like 10 to 1. No, I'd be cautious of this to solve that. If that thing was, if L was 10, I'd say fine, no problem. Why is that condition on there in the first place? Well, look at this picture. Did we ever account for the heat loss out of the front and the back? No. No. Well, what are you supposed to do? Well, if L is really, really long, much greater, how much heat's lost out of the front and back compared to the four sides? It could be negligible. Could be a matter of fact, the bigger L is, the less air you've got in the solution. So in our case, this is probably not a good example here, but that's okay. You see the method to solve the problem is the important thing. Question back there somewhere?
We're talking about the R convection outside.
Yeah.
We got a different value when we plugged it in.
Yeah, I got two different ones too. I tweaked the problem myself from the textbook, and I have different numbers. So
Okay.
don't worry about the numbers,
Right.
the method. Look at the method. Okay, if you're right, yeah, it is. I changed some dimensions and I used the old numbers in this problem. So yeah, these numbers probably aren't perfectly true. I know they're not. Okay, so combining chapter 4, here it is, with chapter 3, here it is. The exam Monday will cover only chapter 3, that stuff, not this stuff, just so you know. Okay. All right, before we do the last part of chapter 4, let me go back and look real quick at some of the homework out of chapter 3, and I'll mention a couple of things you should do and should not do. I'm going to go back to chapter 3, and I'm going to look real quick. Let's see which one. Where it is. I'll draw a picture here. And again, just so you know, for the exam, I told you, 4 problems, 3 chapters. I've got old exams on Blackboard. You've got your data package on Blackboard. The data package has everything for the whole quarter on it. So there's stuff on radiation and convection, chapters 6, 7, 12, and 13. Doesn't matter, ignore them. Look at what I give you from chapters 1, 2, and 3. Okay. Office hours Monday, normally 8 to 9. I'll make it 7 to 9. 7 to 9 Monday, 2-hour office hour. If you have any questions after today's lecture, before the weekend, I'll be in my office from 11:35 to 12 noon, so you can swing by, ask me any questions then too. Okay, now let's talk about problem 111, a solar collector panel. Okay, on that panel, okay, here's the problem. The base temperature, there's tubes carrying hot water. The water in the tubes is temperature T0. That's the base temperature of the fin between those two. The solar collector is a fin problem. This is a solar collector. We have heat transfer coming in. I think it's called Q radiation double prime, something like that. On a solar collector. Yeah. Mm-hmm. Right. I'm going to put both problems down at the same time. Problem 3.116. We have a thin metallic wire passing an electric current through the wire to produce a uniform volumetric heat generation Q dot. The ends of the wire at X plus or minus L are maintained at T infinity. The ends of the wires are maintained at T infinity. All right, the wire generates Q dot. Now, all I want you to do in those problems is to derive the correct differential equation
with the correct boundary conditions. That's all. Derive the differential equation with the correct boundary conditions. To do that, you go back and start on equation 361. That's the basic derivation for a fin. That's the first thing in the fin part of the chapter. The picture on the top of page 157 is the same. It's a round fin here. It's like a wire. All you do, I'll just write down what it is. That's what it is on both. And that's for a thin piece of the fin that looks like that. We did that, you know it, you'll see it. That's for a thin piece of the fin that looks like that. That is question. So, on this problem here, what's new? What's new is that guy right there. So what do? Is that coming into or going out? Because remember now, energy coming in is on the left. Energy going out is on the right. That's energy in. What do? You put this guy right here. Qx plus Q radiation double prime. Okay. Is it a constant? Oh yeah, it's just a constant. It's a number. I don't know, 1,000 watts per square meter. It's a constant. You add that constant to the left-hand side, clean up the differential equation, so when you're done, it looks like the equation at the bottom of page 157. Clean it up. This one. You know, this thing looks like the one back in the first part of the chapter, but now there's heat generation. You know, guess what that is? Are you adding or taking out heat in the little element right there? You're adding heat. Which side of the equation does adding heat goes out? I remind you. This is all the terms which add heat to that little element. These are the terms that heat goes out of the little element, or energy. We're adding energy, so what do? You add Q dot on the left. Is it a constant? Of course it is. It's a constant. You're adding a constant to the differential equation. That's all you're doing. But watch out.
Now, don't forget, this is watts per cubic meter. Multiply it by the volume. This is watts per square meter. Multiply it by the right area. Yeah, by the right area. Where's the right area? Where does that radiation hit the solar collector? Right there. That's the area. Okay, and when you're done, here we go again, go through page 157 and make it look like the equation at the bottom of page 157. Clean it up. And then add the correct boundary conditions. How does this picture look? Looks like that. How does this picture look? Oh, it's hot there. What's the boundary conditions? When x equals 0, well, I won't tell you, but you can find out what it is, okay? At x equal here, guess what the one which is hard to get? dt dx at x equal L equals 0. dt dx at x equals 0 equals 0. Now I just did the boundary conditions for you, but that's okay because That's all I want you to do. On the exam, that's all I ask you to do. Derive the correct governing differential equation and tell me what the boundary conditions or initial conditions are. Boundary or initial conditions. But don't solve it. That's way too hard for a 65-minute exam, obviously. Okay, the last one. The fins attached to a wall. For the fins attached to a wall, the problem you have looks something like this. Okay, the fin thickness is 1 millimeter. No, I think it's a half, if I remember right. Let me just check it real quick. Okay, 142. There it is. Half millimeter thick. Okay, so you use the equation that I told you about, equation 3105. It has QF, N, A to F, AF, H, T base minus T infinity. This is in your notes. Plus the wall not covered by the fins, H, A base wall, TB minus T infinity. There it is. You can get A to F whatever way, table or the graph, table or graph. You're given H, you're given TB, you're given T infinity, you're given H, you're given TB, you're given T infinity. AF is the area of one fin, The top, the bottom, the front, the back, not the tip. The top of the fin, the bottom of the fin, the front of the fin, the back of the fin, but not the tip. Area of the base is the area not covered by the fins. So what do you do? How big is this thing? How big is it? He didn't tell you. So what are you going to assume? Well, most people say, you know, I love the number 1. It's so simple. I'm going to make the area 1 by 1. Oh, smart move. 1 meter by 1 meter. Why not? Nobody told me. I'm going to assume 1 by 1. Makes life a lot easier. What's the bare area for the whole? Now, this is with fins. Q, no fins. There's the wall, 1 by 1. What's the area of the wall? 1 times 1. Oh yeah, that makes life really easy. The area is 1 square meter. There's no fins. Okay, let's find out N, how many fins there are. Okay, the fins are stacked vertically, like this on the wall, stacked vertically. How far apart are the fins? Okay, the fins are spaced apart, he tells me, by 4 millimeters. Number of fins, 1 meter vertical. Fin spacing, 4 millimeters. Fin spacing. 250 fins on my wall, 1 by 1. 250 fins on my wall, 1 by 1. What is the area of the fins? Take the area of 1 fin, multiply by 250. 250 times the area of 1 fin. What's the area of the fin? Well, I'll tell you. Let's see what L is. Fins are 50 millimeters long. Two, top and bottom. Top, L, okay, times into the blackboard. Okay, so here's the fin. Okay, this is 1 meter here. Here's the top of the fin. What's this distance here? 1 meter. How far out of the board? L sub C, not L, L sub C, to times L sub C times 1. That's the area for one fin. Base area, the base area is the total of all these base areas here. So take the 1 meter minus 250 times 0.05. And that's the area of the base. Goes right there.
Instead of guessing the width, you could also leave it as a variable.
It cancels out. It cancels out. Yes, you can. Yes, it can. The reason why it cancels out because your percent increase is equal to Q with fins minus Q no fins divided by Q no fins. So every term has that unknown length in there. So yes, it will. All right, so anyway, just so you know how to find those areas. Now, don't forget, this is what people don't understand. He said that the fins are equally spaced at 4 millimeters. He says the fins are equally spaced at 4 millimeters. That does not mean that this is 4 millimeters. No, it means center line to center line is 4 millimeters. Someone said the studs in that wall are on 16-inch centers. What does that mean? From the center of one stud to the center of one stud is 16 inches. Fins are equally spaced by 4 millimeters. What does that mean? They're equally spaced center line to center line, 4 millimeters. So what's the space now here to here? 3.5 millimeters. Some people make that mistake and get the incorrect answer. Okay, big long story, but that way we all are on the same page. All right, now we're going to look at the last half of chapter 4, which is the numerical approach to 2D conduction. Okay, so we have numerical approach to 2D conduction. We have some homogeneous body, thermal conductivity K. We're going to model that for numerical analysis by a grid which has, break it into nodes. And these nodes are spaced apart by a distance delta x and a distance delta y. So we replace a homogeneous material with a model, and the model has the mass lumped in nodes, and they're connected, so these are called nodes, and they're connected by heat conducting rods. Nodes connected by heat conducting rods. We take the nodes out and we call the center node node MN. Okay, so our nodes M, let's take the left-hand one, M minus 1N, M plus 1N, node M, N plus 1, and node M, N minus 1. So row and column, row and column. Row M, column M, row N. Okay, now, the only way heat's conducted is through these fictitious heat conducting rods. That's our model. So we write energy balance on the center node. And we write it a little different than we have in the past. We say the sum of all the heat flows into node Mn must be equal to 0. A lot of times in electrical engineering, we'll have some circuit, and if you don't know the current in this circuit, whatever it might be, I'll make up something fictitious here. And this node right here, sometimes to solve for the unknown currents in a DC circuit theory, you'll say, I'm going to write the nodal equation. The sum of all the currents into that node are 0. Why do you do that? One reason, because you don't know when you start which way the currents are going. You don't know the current direction when you start. So, to be general, you say, all right, I know. The sum of all the currents into that node must be 0. Now, I know some are going to be negative. Current here might be minus 5 amps. The current here plus 5 amps. I don't care. I write the sum of the currents into the node equals 0. And then I solve those equations for every node in my problem, a multi-node problem. Same thing here. Since we don't know which way the heat goes, we say in general we know that when I sum the Q's into that center node, it better be 0, which means some currents come in, and when I'm done, some currents are negative value. Okay, but in general, when I start, assume they all come into a node. All right, start here. Into means this is hot then. Okay, so temperature, let's do Ka delta T over delta X. Ka delta T over delta X. So K. The area is here to here. That area is delta Y times, I'll call the depth into the board 1. Okay, and then delta T, T m minus 1 n minus T m n, divided by the distance I traveled. I traveled distance, delta X. That's the first term. Now, from the right-hand side, K delta Y times 1 times T m plus 1 n minus T m n divided by the distance I traveled, delta X. Now from the bottom to the center, K, the area is delta X times 1, T m n minus 1 minus T m n divided by the distance I traveled, delta Y, plus K from top to center node. Area is delta X times 1. Temperature T m n plus 1 minus T m n divided by the distance I traveled, delta Y, equal 0.
Is there a plus in front of the first?
I'm sorry?
There's a plus in front of that?
Oh, yeah, there sure is. Thanks. Yeah, thanks. Okay, now I'm going to say, I'm going to make life easy. Let this be a square grid. Delta X equal delta Y. Let it be a square grid. That's good, because now delta X, delta Y, delta X, delta Y, delta X, delta Y, delta X, delta Y, they disappear. Now I say, you know what? Every term has K in it. I'm going to divide through by K. Divide through the whole equation by K. Gone, 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 gone. Okay, they all disappear. No K's. Okay, now I'm going to write the final result. T m minus 1 n plus T m plus 1 n plus T m n minus 1 plus T m n plus 1 minus 4 times T m n must be 0. This is the nodal equation for an interior node Mn. Every node in the interior of the body has an equation like that. And what it says in words is if you add the temperatures of the 4 adjoining nodes and subtract 4 times the temperature of the center node, if everything's correct, you better get 0. Add those 4 temperatures of the neighbors, connected by a heat conducting rod. The top, add the top to the bottom, to the left, to the right, minus 4 times the center temperature. If things are done right, you should get 0. Now, that's interior node. Now we have boundary nodes, all right? I'm going to put the boundary nodes over here because it's on a table. The nodes on a boundary are much different. And you can derive them. Matter of fact, you will derive them for homework, okay? So they can be derived the same way as I derived that one over there. We're going to go to table, let's see where they are, table 4.2. I'll put one up there for you. Here it is. Okay, there's 1, 2, 3, 4, 5 different nodal equations, table 4.2. It's titled Nodal Equations. And I'm going to show you one here, which is a boundary node. This is for a node on a plane surface with convection. And that's really case 3. So I'm just going to show you one case. There's a total of 5 cases in there. This is just one case. So here is again with the Mn coordinate system, case 3, 2t m minus 1n plus t mn plus 1 plus t m n minus 1 plus 2h delta x over k t infinity minus 2 times the quantity h delta x over k plus 2 TMN equal 0. So that can be derived just like I derived this one over here for a boundary node with convection. That's a boundary node with convection. Okay, so let's look at an example. Let's put the example, I'm going to save this equation. Let's put the example over there, start over there. Okay, we have this plate. And I'm going to use the finite model for this plate. Let's see, we've got 3 nodes there, and there, and there. So I'm going to break this plate down into nodes and heat conducting rods. Nodes and heat conducting rods. The delta x and delta y of my plate, I think, is 1/10 of a meter. Let's make sure. Yeah, 1/10 meter. delta x equal delta y equal 1/10 meter. So the plate is 2/10 meter by 3/10 meter. And the material has a K of 25. It's some metal plate. K is 25. I don't know how thick it is. I'm not going to use that right now. I'll assume 1, because I assume 1 over there. Okay. Now, the bottom of the plate is given to be adiabatic. The left-hand side of the plate is kept constant at 0 degrees C. The top is kept constant at 100 degrees C. The right side is kept constant at 100 degrees C. And of course, we're asked to find the temperatures, the temperature distribution in this model. So, find the temperatures. All right, so now, there are a total of 3, 6, 9, 12. 12 nodes. Okay, so first of all, I'm going to put down the temperatures. I know the temperatures of some of the nodes, for sure. Oh, I better, first of all, number the nodes. Generally, unless it's a humongous, big part and you have thousands of nodes, it's best to just number them 1, 2, 3, 4, 5 rather than double subscript. So this is such a simple problem. I'm going to call this node 1, this node 2, this node 3, and so on. Okay, so let's put down the temperatures we know. T4 equal T7 equal T10 equal 0 degrees C. Okay, T2 equal T3 equal T6 equal T9 equal T12. Let's make sure. 2, 3, 6, 9, 12. Yeah, equal 100 degrees C. T5, 8, and 11. T5 and T8 and T11 are unknown. Right, okay. So, I've got 3 unknown temperatures. Okay, yeah.
What about T1?
T1. Try and play this game with a friend of yours who's not an engineering or science major, okay, or math major. Can't be science or engineering major, okay, because they'll know the answer too quick. But here's how to impress your friends, you know, that you're a real math whiz. There's Y, there's X, there's 0, there's 4, there's 10, there's 2. Ask this guy, say to him, here's a graph X and Y. You probably had that when you were in high school. Tell me the value of Y when X equal 4. And the guy says, it's 2. Then you say, oh, hey, wait, look, let's ask Henry. Henry, look at that graph. What's the value of Y when X equal 4? Henry says, oh, not a problem, 10. I said, whoa. I said, wait, you said 2, you said 10. One of you guys is wrong. No, they're both wrong, of course. They're both wrong, of course. What's the answer? There is no answer. In math, it's indeterminate. It's indeterminate. Don't ask the question. I can't tell you the answer. Don't ask me the question. It's a mathematical thing. Guess over here now. I asked Joe. Joe says, well, that's pretty obvious. It's 0 degrees, 0 degrees, 0 degrees, 0 degrees, 0 degrees, 0 degrees. I said, no, okay. Phil, how about you? He said, oh, no. 100 degrees, 100 degrees, 100 degrees, 100 degrees. I said, whoa, guys. You said 100. You said 0. You're both wrong. Don't ask me the question. I can't tell you the answer. It's indeterminate. indeterminate. Conclusion? If you want to, just say T1, indeterminate. Well, in reality, what does that mean? That can't be true in reality. Well, here's what happens. If you put a temperature transducer on a plate like this, all the heat's going to go from just to the right of that point 1 to just to the below point 1. It's called a short circuit in electrical terms. If this were a copper plate, this is 100 volts and that's 0 volts, all the current would flow right where my fingertip is, and there'd be no current out here at all. It's called an electrical short circuit. This would be a thermal short circuit. All the heat would go from 100 to 0 right where my fingertip is. You can't allow that to happen electrically or thermally. So what do you do to get around that experimentally in a lab? You take a little square piece of insulation for the electrical problem and put that little square piece of insulation up there so they can't touch each other. That's the point. Make it so they can't touch each other. What would you do here? Put a little thermal insulator right there so they can't touch each other. The 100 degrees won't touch the 0 degrees. Otherwise, you got a short thermal circuit. Okay, so now that's T1. Good question. I'm glad you asked it. Okay, now, so 3 unknown temperatures. That means 3 equations. Here we go. The interior node, node 5 equation. What does it say here? It says, add the 4 temperatures of the surrounding nodes, subtract off 4 times the temperature of the center node equals 0. Temperatures of the surrounding node, node 5, left-hand side, 0 degrees. Node 2, 100 degrees. Node 6, 100 degrees. Node 8, unknown, minus 4 times T5 equals 0. Take node 8 equation, interior node. Okay, start left hand, T7, 0 degrees. T5, unknown. T9, 100 degrees. T11, unknown. Oh, T9, pardon me, T9. Let's see, T5. Oh, I got my T9. Okay, my T9's known. T11, I was right the first time. Minus 4 times T8 equals 0. Node 11. Boundary node. With convection. No, with adiabatic boundary. You go to our table, because the table gives you the boundary nodes. Okay. Now, in the table, in very fine print at the bottom of the table, if you read real carefully, it says, if the boundary is adiabatic in the equation, set H equals 0. Okay, big hint, thank you very much. It says, if you've got an adiabatic boundary in the equation for that node, set H equals 0. 0. Okay, there it is. 2 times T m minus 1 n. That's T8. Plus the neighboring nodes, T10, T12, T10, 0, T12, 100. Minus 4 times T11 equals 0. Okay. Three equations, 3 unknowns. Solve. For your special computer problem 1, it'll probably, I think it's a 12 by 12. 12 equations, 12 unknowns. You can use your TI. There's 2 ways. The solver function, or matrix inversion on a TI. Either way is fine. You can use MATLAB, MathCAD, Theorist, blah, 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 Excel, whatever you want to do. Doesn't matter for your computer homework problem. Doesn't matter. You've got 3 linear equations. Solve for the 3 unknowns. Bam, bam, bam. T5, 63.5. T8, 53.8. T11, 51.9. Okay. If those numbers, and they're not, that's really a very coarse grid. If those numbers aren't good enough, and they're not, it's too coarse a grid, make the grid size smaller and get more accurate answers. Okay, I'll make the grid size 5 centimeters. That's 10 centimeters. I'll make it 5 centimeters. Okay. Okay, unknown temperatures. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, this was 3 by 3 matrix inversion. Now it's 18 by 18. Now you do that again. You want to make, you do that again. Say, I'm going to make a half that. Oh wow, 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 wow. It just blows up real fast. Or you'll get better answers, but you wait a long time on your TI. You say, my TI must be broken. No, it's not broken. It just takes it a long time to do that. 12 by 12 takes it a long time to do it. The solver functions quicker usually on a TI. Anyway, yeah, to get a better sense of what the temperatures are, make the grid size smaller. In the limit, as the number of nodes goes to infinity, you'll approach the exact solution of the governing partial differential equation. But who wants to wait that long? The benefits economically, cost-wise, it's not going to pay off, so you don't do that. Okay, now one last thing. What if someone says, I want you to draw a flux plot of that? Okay, this is Monday, so okay, I'm going to draw a flux plot of that. Okay, the bottom is adiabatic. This temperature is T1, this temperature is T2, this is T2. We'll assume T1's hotter than T2, just it makes more sense. So, okay, draw the heat flow lines. Obviously, one goes from hot temperature to cold temperature. Upper left-hand corner, it almost makes a quarter circle. Right angle, right angle. At the bottom, the heat that leaves T1, high temperature, goes towards T2, but it can't get out the bottom. So near the bottom, it almost goes straight across. Okay, now I've drawn heat flow lines, or what they call adiabats. I've drawn adiabats at the 2 extremes, upper left-hand corner and near the bottom. Now it's pretty simple to fill in the rest. This guy must come out, he must go in here, of course. This guy comes out, if you want, it's your choice. I'm going to try and bisect that angle. Okay, there you go. Then this guy comes out, he goes over there. This guy comes out, and he goes over there. Right angle, right angle, right angle, everywhere. On the boundaries, rule 4. There's the heat flow lines. It's somewhat intuitive. I mean, yeah, it really is. Now comes the harder one. Show me the isotherms, the constant temperature lines. Okay, here's the rule we had before. Anytime you've got a corner where 2 temperatures come together, different temperatures come together, the isotherms fan out from that corner. They fan out like this. If the temperatures are different in the corner, in this corner upper right, the same temperature. No. This corner, temperature, left-hand corner, yes, temperatures are different. Isotherms fan out. So take the easy one first. This guy comes out here, crosses at right angles everywhere, and goes into an adiabatic boundary at a right angle, and so on, and so on, and so on. Everywhere inside, they must cross at right angles. Okay, there it is, the isotherms and the adiabats. It kind of gives you a sense of the heat transfer and where the isotherms are. So it gives you some physical feeling for the problem. This stuff here is called mathematics. You don't always get a physical feel. When you see a spreadsheet, not many engineers get excited staring at a spreadsheet. Oh no, I put you to sleep after lunch in a technical meeting. No, that doesn't excite engineers. You show an engineer a graph, oh wow, their eyes just pop open like, what's that graph supposed to be telling me? I don't understand that graph. Oh yeah, we get excited about graphics. Oh, this is the truth. Excel's the truth. But this is what we engineers sometimes, that develops our intuitive feel for a problem. Intuition. Okay, good stopping point. Get a good weekend of rest, haha, and we'll see you Monday morning.